All right, good. So today's class, we are going to finish up the module on electrostatics. We're going to talk about dielectrics, and we'll talk about electrostatic fields at boundaries, and then we'll talk about capacitance and capacitors and electrostatic forces. So in the interest of time in this class, we are not going to be doing some of these electrostatic boundary problems that you've seen. Really, the way to solve these things more commonly is to use simulation tools, and we've already talked about how you can use COMSOL to solve electrostatic boundary problems. So this is, in some ways, has been covered during the other sections. So the goal of today is to cover dielectrics first, and then talk about the rest of these items. So where the context is there's two types of electronic materials. Conductors, you can form an electric current going through them. Dielectrics, you can't get any current, but you get a strong electric field due to a polarization effect. Conductive materials make resistors and conductors. Dielectric materials make capacitors. All right, and as you know, like both of those elements are very important in terms of electronics. In particular, the important thing about capacitors is that they can store energy. So we're going to talk about capacitance and energy storage there. And they can also create an electrostatic force, which wasn't that important maybe 15 years ago, but they've become extremely important now because of the MEMS and micro actuators that are used in today's airbag deployment sensors and accelerometers that are all in your cell phones. They're quite ubiquitous. So let's get right to it. I'm going to scroll ahead here. All right, we're going to start right from the fundamental concept. Okay, and again, when you have questions, please feel free to jump in. So we're going to talk about dielectric materials today. What defines a dielectric material is that if you put a voltage across it, then the material polarizes and it creates an electric field within it. So this is the basis of how a capacitor works. But before we get into that, we're going to talk about the materials themselves. All materials, so that we look at the general material, which is not polar on its own, it can become polar in an electric field. So let's look at how that works. Our mental model of solids is that solids are composed of atoms, and an atom has a positively charged nucleus, and it has a cloud of electrons around it. Okay, depending on the degree of sophistication of your model, you can think about electrons orbiting the nucleus, kind of like planets orbit the sun. If you think about it more in terms of the quantum mechanical model, there are like various shapes of electron clouds around the nucleus of the atoms, and the shapes are governed by quantum mechanics. How you view it isn't quite all that important in this sense. But what you do need to know is that nonpolar materials has a symmetry to it. So there's a symmetric electron cloud around the nucleus when there's no electric field. But when you have an electric field on there, what happens is that the material polarizes. And what polarization means is that there's this thing called an electric displacement. At the atomic level, what that means is that the center of the electron cloud is moving in one direction, it's moving opposite the field, and the positively charged nucleus is moving in the same direction as the electric field. So if your electric field is pointing from down to up, your nucleus, your positively charged nucleus, is going to be displaced upwards, and the center of the electron cloud is going to be displaced downwards. Because of this displacement, you end up with a dipole-like effect because you have a separation of charge. Okay, so what this ends up looking like is a created dipole. Okay, an induced dipole is what they call it, an induced dipole, a dipole that is induced by an external field. So you have what looks like a sort of a positive charge on one end, a negative charge on one end, and the amount of polarization you get is called the displacement. Okay, So now the material acts as a dielectric material, and the polarization is by this phenomenon called electric displacement. Now there are other types of materials, for example water, which are polar by nature. This is, as I said here, this is an example of a nonpolar material. So on its own, there's no polarization. There's no dipole effect. But other materials already have a dipole effect built into it. For example, the water molecule. If we look closely at a water molecule, you're going to see that it's composed of an oxygen molecule and two hydrogen molecules. You don't need to know this for this class, but if you recall from chemistry, you'll recall there's this concept of electronegativity. Certain atoms, like oxygen, pull really hard on electrons. The electrons like to be with oxygen. Molecules like hydrogen, on the other hand, they have weak electronegativity. So what happens is that the oxygen steals more of the hydrogen's electrons, like so, and so the oxygen molecule acquires a negative charge, and the hydrogen, which has lost its electrons, acquires a sort of a positive charge. So just the molecule on its own has a dipole associated with it. And that's why this is called a polar material, whereas this is over here is a nonpolar material. So generally, when there's no external electric field applied, these polar molecules, the orientation of the dipoles is just in any random direction. So you can think about the water molecules just being in any random direction, and they're moving around quite rapidly. But when you apply an external electric field, then they all align to the electric field. So the electric field is pointing upwards, so the positive charges like to move in the direction of the electric field, so they align this way. The negative charges move in the opposite direction. And so you get this effect where all the molecules line up to the field, and this enhances the electric field within the device, within the material. Or I should say it enhances the displacement field within the material. Okay, so the lesson to take away from this slide is that these polar materials have a stronger dipole effect than nonpolar materials, and as a result, polar materials tend to have a higher dielectric constant than nonpolar molecules. When a material has a higher dielectric constant, it means that they have a stronger polarization effect when they are aligned in the presence of an external field. Now, I want to clarify one thing because this is often a point of confusion for students. How many of you, let's have a show of hands, like how many of you think of, here, let's do a poll here. Yes or no? How many of you think of water as a conductive material? You can answer yes if you think of water as a conductive material, and no if you think about it as a dielectric material. So again, the question is water a conductive material? So answer yes if it is a conductive material, and answer no if it is a dielectric material. Song says water plus electrical kills people. So what does that mean, Song? Does that mean water is conductive or non-conductive? Water is not a conductor, good conductor, Joseph says. So there seems to be just some disagreement here. So this is interesting. The class is almost evenly split. There's 8 of you who say, yes, water is a conductor, and no, water is not a conductor. 9 of you say that. Sang, are you volunteering to test it? Okay, so water on its own is actually a really good dielectric material, as you can see on this slide here. So what is the reason? Dielectric materials don't conduct electricity, right? So why does water, why or how does water become conductive? Why is water a good conductor? Exactly, yeah, Siva's got it. There's ions in there. We can never have perfectly pure water with no ions in there. If any tap water that you get will have tons of ions and minerals in it, and those ions are conductive. They can conduct charge. The simplest ion one might be like some salt. You might have some salt in the water, and that's highly conductive when it becomes when you have salt in the water. So the only way you can get really dielectric water is to have completely deionized water, and that's actually pretty hard to do. It has to go through a reverse osmosis process, and even then it's very hard to keep the ions out. Deionized water is used in the semiconductor industry, by the way. But the point is, getting back to here, is that polar materials, like water is a really good polar material, and it becomes a very good dielectric material only if there are no ions in the water. Even if there's a small concentration of ions, water becomes it becomes conductive, and this polarization effect is mitigated by the fact that you have these mobile charges. So water can't even support an electric field because it behaves more like a conductor. Yeah, Siva made a good point. Di water is the one that actually behaves like a dielectric. And if you do get pure Di water, the dielectric constant for Di water is something like 80. It's very, very high. Whereas most materials have relative dielectric constants between 1 and 5. So in any case, let's use that as a segue into the discussion of dielectrics and then polarizability. We'll get to that. All right, so what happens? Let's say we have a capacitor. So I'm just going to, imagine that we have a voltage here and we have our electrodes here. We have an electrode like this and an electrode like this. Okay, and we put an electric field over a dielectric material. Okay, I'm going to just undraw what I just drew with the voltage source, because I just want you to see how you actually apply a field over the electric material. You take a voltage source and you connect a wire on one end, wire on the other end. You get this electric field, but what happens in the material? All the dipoles, the permanent dipoles or the induced dipoles, they line up to the field like this. Okay, so you imagine the molecules actually rotating so that they align to the field, or the induction effect that I showed you earlier. And what ends up happening is you get an electric field inside the material, and you get a positive surface charge on one of the surfaces, because you can see that the way that these atoms are arranged, the positive charges are on the top. So if you look at exactly the top surface of the material, you're going to get a positive charge on the upper end. And if you look at the bottom surface of the material, you get a negative charge on the bottom surface. Okay, so the surfaces become charged, and that's called a polarization surface charge, rho s for short. Okay, and this is all because the molecules have aligned to the electric field. So how do we actually quantify that? So there's this concept of polarizability, susceptibility, and relative dielectric constant. So there's a lot of different terms here, but they all have to do with the same effect. You put an electric field on there. How do we quantify how much the material polarizes in response to that field? So as you recall, when we at the beginning of class, when we talked about Maxwell equations, we said that there's two quantities that describe electric fields, E and D. And this displacement becomes very important now. We just mentioned that a couple of slides ago. So before this, when we've been doing all our homework problems on electric fields and things like that, we've been talking about E, which is the electric field intensity, and the units for that is volts per meter. This is what we commonly think of as the electric field, and this is the field that forms when there are charges in space. You get electric field pointing from positive charges to negative charges. Okay, electrical displacement, or electric flux density, the units for this is coulombs per meter squared. Okay, coulombs per meter squared is, you can think about it as kind of like a surface charge density. We said here that when you polarize the material, you start to get a surface charge on the top. Okay, and the units for surface charge, as you remember, Units for surface charge is coulombs per meter squared. Okay, so this electric displacement also has units of coulombs per meter squared. So that may help you intuitively remember the units for electric displacement here. And this D basically describes the displacement effects of an electric field on the charges within the dielectric material. There's another quantity P, which describes the ability of a material to displace due to the applied field. So let's look at E and D first. And so just recall from the basics, Gauss's law. Remember that Gauss's law was in terms of D, not in terms of E. Okay, so del dot D is equal to rho V. This was Gauss's law. Now, early on we said a simple relationship for D is D is equal to epsilon E. And that is what we're going to essentially derive here. Okay, so you can see that D is equal to epsilon 0 times epsilon R times E here. So the two are related by just some proportionality constants. The electric displacement is proportional to the amount of electric field that you place in the material. But let's look at some of these other quantities in the middle here. Let's see what that's all about. So the electric displacement D is equal to epsilon 0, which is the fundamental constant. So let's just put an arrow here. This is the permittivity of free space. So vacuum. And this is equal to 8.85 times 10 to the negative 12 farads per meter. That's a fundamental physical constant. You multiply epsilon 0 by the electric field. Okay, this is the displacement that you would get in free space. Okay, this extra P, this is due to the material. Okay, so if you have pure vacuum, then D is equal to epsilon 0 times E, and your polarization, you don't have any polarization in a vacuum. But if you have a dielectric material in between that can polarize or align to the field, then you have this P, polarization parameter. And so D becomes equal to epsilon 0 times E plus this polarization effect. Now this polarization effect can be described by a constant called the susceptibility. Polarization is equal to epsilon 0 times the susceptibility E. This is a constant for a given material. That depends on how polar it is, how polarizable it is, and then you have the E here. Okay, so so you have epsilon 0 times E, and then you have this term which is also a function of E. So you take the E out here, and you're left with epsilon 0 over 1 plus the susceptibility of the material times E. This is a material parameter. All right. Another way that we can define the susceptibility or polarizability is not to use X sub E, but we can use a relative dielectric constant, E sub R. So this E sub R, this relative dielectric constant, is equal to 1 plus the susceptibility of the material. Okay. So let's quickly review what these physical intuition is here. When you apply an electric field to a material, it's going to polarize. The amount of polarization is proportional to a fundamental material property called X sub E. This depends on the material that you have. Okay. Epsilon 0 is not material specific. Okay, that is a fundamental constant. So if you want to express, if you want to look at how much the electrical displacement for a material depends on the electric field, you can think about it in terms of susceptibility, and you can use this equation here, or you can think about it in terms of the relative dielectric constant, which is the one that you see here. And this is the one that's most often used. Okay, most of the time when we're dealing with these types of problems, we just talk about the permittivity of the material. We don't use a susceptibility. So for dielectric materials, the polarization is going to be non-zero, X sub E is going to be non-zero, and epsilon R is going to be greater than 1. For conductive materials, the polarization and the susceptibility are both equal to 0, right? Because in a conductive material, the charges just move. You don't have molecules aligning to the field. The charges just move, so there's no polarization, and epsilon r as a result is equal to 1. Okay, the epsilon r is not equal to 0. Keep that in mind. It's equal to 1. So for a conductive material, d is going to be equal to epsilon 0 times e. And for a dielectric material, you're going to have to also include this epsilon r constant. Any questions so far? Or just give me a thumbs up if you're good. Sound okay? Good. All right, good. So let's just do a quick example so you can think about fields and dielectrics. Suppose we have a positive charge in the middle of a spherical dielectric. So imagine that we have a hollow sphere like this. And this is a shell. Okay? Now, so this is made up of a dielectric material. Now we say we're going to put a positive charge right in the middle, in the interior of the shell. This is air inside. This is a dielectric material surrounding it. And we just somehow put a small charge in the middle of the shell. So the question is, how are the charges distributed on the inner and outer surface of the shell? So just so everyone knows, this is the inner surface. And this is the outer surface. Okay, so I'm going to just start the poll here. So there's 1, 2, 3, 4, 5 choices. So you can go ahead and put in your thoughts. Okay, let's wait. We have 14 of you responding now, 17. So let's wait for a couple more. Okay, good. All right, so looking at the polling results, 10 of you said D, 8 of you said C, and 3 of you said B. So most of you, about 45% of the class, chose D. The correct answer is D. So let's look at why that's the case. So the way that you would attack this problem, you think about just which direction the electric field is arranged. So we can just draw the electric field right like this. I'll draw it in blue. The electric field, as you know from a single point charge, the electric field just points away from that positive point charge. It points in this direction. All right. So the electric field is going through this dielectric shell. So when the dielectric material aligns to the field, we just, oops. So you're going to end up with positive charges on this surface, just like we saw on the previous slide, and negative charges on this surface. So the inner surface is going to be negative, and the outer surface is going to be positive. So A and B are both incorrect because you have a dielectric material, you have a charge distribution, different charges on each surface. Part C is incorrect because it's the opposite of what we're looking for. And E, no charge on either surface. This is not true for a dielectric material. If you take a dielectric material and you put it in an electric field, that polarization effect will always result in a surface charge. That's the thing that identifies a dielectric material. All right, so let's talk about the relative dielectric constant then. So we said that E sub r is the most common one that's used. So we have this very simple relationship. D is equal to E0 times ER times the electric field. So we're going to talk about what ER is, because we know E0 is this permittivity of vacuum. That's a fundamental constant. So E sub r depends on the material, and the higher that E sub r is, the more polar the material tends to be. So you can see that materials like air, which are not, essentially non-polar molecules like nitrogen and oxygen, remember, water is polar, but oxygen on its own is non-polar. So vacuum has the lowest, obviously. Air is a little bit larger, mostly non-polar molecules. Then you get to things like glass, mica, and mylar. These are some materials that are often used in capacitors that you may have in your lab. These are, things like Teflon, for example, has a low dielectric constant because it's pretty non-polar. Something like water has a very high dielectric constant because it's more polar. And the highest one in this list is a material called strontium titanate, which I'm not too familiar with, but it has a very, very high dielectric constant of 310. So the higher the dielectric, you can have large capacitances. C, if you recall, for a parallel plate capacitor, C is equal to epsilon A over D. So if you want to build large capacitors, you choose a material with a high dielectric constant and a large area and a small gap between the electrodes. But this is one of the knobs that you have to work with as an engineer. All right, so good dielectrics have E sub r exceeding 100. Just a few things about homogeneous materials and isotropic, anisotropic. In an isotropic material, epsilon r is the same in all directions, but in an anisotropic medium, ER depends on the direction. So there are a lot of electronic materials that are built from crystals. Silicon happens to be one of them. Semiconductor materials that are used in making computer chips and things like that. So when you have a crystal material, you can actually have different properties in different directions. We're not going to be talking much about that in this class, but we talk about it at length in 4570, which is another class that I teach in the department. So if a material happens to be both homogeneous and isotropic, homogeneous, by the way, epsilon r is the same everywhere. If it's homogeneous and isotropic, it's called a simple medium, and we're going to be dealing with those in this class. So let's go ahead to another topic, dielectric strength and dielectric breakdown. So insulators generally don't allow charge to move through them, but if an electric field is strong enough, an effect called dielectric breakdown occurs. And the way that you can think about dielectric breakdown is, I'll just here. The way that you can think about dielectric breakdown is that imagine that you have an atom, and inside the atom you have a positively charged nucleus, and then you have these electrons in this cloud. All right, so if you place this in an electric field, then as you know, that the electric field is pointing in this direction, and the positive charge goes up here, and the there's more negative charges at the bottom here. So the center of mass for the electron cloud goes down like this. Now, what if you were to take the electric field and make it super strong? Very, very strong electric field. So the electric field exceeds the dielectric strength of the material. So E is greater than the critical electric field. So when that happens, this effect happens where the electrons one of these electrons can actually get torn away from the atom. All right, so in a moderate electric field, you're just kind of moving the center of mass of the electron cloud in a direction. But if you make the electric field really strong, you can actually rip electrons away from the atom. And this process is called ionization. All right, some of you have heard the term corona discharge. Lightning is another example of ionization. This is an example where the electrons get ripped away. And when the electrons get ripped away, it creates a plasma-like state of matter. And plasmas tend to be conductive. So plasmas, you may have heard about plasmas, are important in, like the solar system when you're looking at the effects of the sun and things like that. These are some examples of dielectric breakdown. So in a lightning storm, what you have is you have in a lightning storm, you have a cloud. Actually, there's an example of that on the next slide. Yeah, I'll get to that in a second. So lightning is one example. Another example is if you were to take, positive charge here, negative charge here, so your electric field is pointing in the right direction, left to right. So this is air in between these two electrodes. So these two things are electrodes, just metal materials. And you get a really strong electric field here, really strong electric field here, and you even get a really strong electric field here. If you exceed the dielectric strength of the material, the whole material in the middle becomes like a plasma, and you get these sparks that flow through. So these sparks are actually conductive paths where because the electrons are ripped away from the material and they're free to move, the electrons can actually travel through and you get a conductive path like this. But they exist for a short period of time and then you get a different one in a different space. The pattern in which these conductive paths happen is actually quite beautiful, as you can see from these pictures here. And sometimes these patterns are called fractals, and you can actually use electrostatic discharge to make beautiful art like this that you can see in this picture. You can click on that link there, and these things are called Lichtenberg figures, so that you might find that interesting. The dielectric strength of air at atmospheric pressure is 3 kilovolts per millimeter, so that gives you an idea of how strong an electric field you need to actually turn air into a plasma. Okay, and that's what happens in the case of lightning. So how lightning works is that you get a cloud up here that builds up a lot of positive charge. Okay, and the lightning rod builds up negative charge. And there is a really strong electric field between them, so the electric field is pointing in this direction. Once that electric field exceeds the dielectric strength of air, then this lightning occurs. The air becomes ionized and the air becomes conductive. You get a surge of current. Now, the reason we use lightning rods to protect from lightning is because essentially, we can't avoid lightning from happening, right? We just want the lightning to go in certain places where we can dissipate that charge safely in kind of like an electrical circuit. So the idea here is that the surge of current will go through the lightning rod, and the lightning rod is connected to grounding structure, so all these charges actually go to earth ground down here without going through all the electrical lines that may be in the building, which would obviously cause a disruption or surges and damage electrical equipment. So lightning rods are often put on top of tall buildings. And from this class, you already understand why that may be the case. Electric field is equal to V over D. The voltage, you can think about this as a voltage of the cloud divided by the distance d separating the two conductors. So you have a buildup of positive charge here, a buildup of negative charge on the lightning rod. And so this d, because the lightning rod is tall, this d is smaller than the distance from the cloud all the way to ground, right? So the electric field, because D1, let's say call this D1, let's call this D2, D1 is smaller than D2, right? And so the electric field, the E1, is going to be larger than E2. So there's a stronger electric field between the cloud and the lightning rod, and a lower electric field between the cloud and the rest of the city. And that's the reason why the cloud why it surges through the lightning rod instead of other random places. And so there's a whole, read about this recently, actually. I thought it was quite interesting, is that there's a whole design principle on how to design lightning rods, and depending on how tall the lightning rod is, how much of an area that it protects around it. And all of these models actually can be simulated using things like COMSOL to find out where the dielectric breakdowns will occur and things like that. So it's pretty neat. It's really all electrostatics here. All right, so we're going to continue on, talk about electrostatic fields at an interface. So we're changing gears now. Excuse me. We're changing gears now, and we're going to think about what happens when an electric field travels from one dielectric material to another. This is a very important electrostatics concept, but in terms of applications, this effect is very important in phenomena like refraction. The bending of light at interfaces are all based on the behavior of electrostatic fields at interfaces. Okay, so there are two rules, and we're going to derive both of them. So the first rule is that the tangential components of an electric field are equal on both sides of the interface. So what we're thinking about here is what happens when you have medium 2 and medium 1, and you have an electric field. Let's say you have like an electromagnetic wave going through from one material to the other. So the question is, does the field change as you go from one medium to another, since you're going into materials with different dielectric constants? And the answer is that parts of the field change. The tangential component of the field, so the component that is tangential to the interface, meaning the interface is this line here, right? The component of the electric field that's tangential to the interface, E sub t, turns out that those are equal to each other. It does not change as you go from one medium to the other. The normal components, on the other hand, the d1n minus d2n, remember this is the displacement field, not the electric field, d1n minus d2n is equal to rho sub s. So it turns out that depends on the amount of charge on the surface. Okay, so the normal component of the displacement field minus the normal component of this displacement field in one material versus the other is equal to the charge density between the two materials at the interface. So the way you can think about charge density again is you can think about, hold on, let me erase this on the slide. So you can think about there being like, a set of positive charges on this interface, or maybe a set of negative charges. So that's what rho sub s means. Okay, and the normal components are obviously the components that are normal to the surface. All right, as you can see here, d1n, d2n. So let's go and derive why those are the case. It turns out we can derive both of them fairly easily using the rules that we have discussed already in this class. The derivation of the first rule, E1t is equal to E2t. Where did my mouse go? Oh, there it is. Okay, so to derive the first rule, we know that the line integral from point 1 to the same point is 0. Okay, so what we're talking about here is we are going to take the integral of the electric field going in a closed contour. Oops. a closed contour. That's what this means, that little circle there. So imagine that you have a rectangle like this. What we want to do, what we're saying is that the electric field, if I start off at A, okay, and I go from A, I'm going to integrate the electric field E dot dl. I'm going to integrate that along its closed contour like this, going from A to B, B to C, C to D, then D back to A. So the integral going from, if you remember from before, actually let me just go to those slides here so that you can, it'll be a good review. When we were talking about voltages. So we talked about the potential difference between 2 points, right? We said that the potential difference between point 1 and point 2, V2 minus V1, is the integral, negative integral of P1 to P2 of E dot dl. All right, so if you went from P1 and you went around in a random path, any random path, but you ended up back at P1, okay, so if you took the integral from P1 to P1, then it becomes the voltage at P1 minus the voltage at P1. Minus the voltage of P1. If you take the integral of the electric field along a path, and that path ends up at the same point, then the voltage difference is 0 between the 2 points, right? Voltage of P1 minus the voltage of P1. This is equal to 0. So the integral is also equal to 0. So intuitively what that means is that from here, if you take the integral of the electric field and you go in any random path that you choose, but you end back up at the same point, then that integral is going to be equal to 0. Because the voltage difference is, you've gone from same voltage to the same voltage. All right, so that's where this rule essentially comes from. So E dot dl going around this loop is equal to 0. So we are going to go in the counterclockwise direction like this. We're going to say that's equal to 0. And this is going to actually help us derive this E1t equals E2t. So the other trick that we do is we say that when we're evaluating this integral, we say that we're going to have some delta L, some length that we're integrating, some length of this rectangle. But this distance here, h, so the delta h is the distance from the width, the height of the rectangle. We're going to make that very, very small. And when we make that very, very small, this portion of the integral and this portion of the integral, going from B to C and from A to D, or D to A, sorry, these portions of the integral become 0, essentially, because delta H is going to 0. Okay, so the lengths of these are so small that the line integral along these lines are basically equal to 0. So in that case, we're just left with 2 line integrals, so A, B, and C, D. Again, we're trying to find the line integral around the closed contour, but we're going to ignore the left one and the right one, because we're going to say that as delta H goes to 0, so as this rectangle becomes very short. So what we're left with is a line integral on the top line going from A to B, and then we also have the line integral from C to D at the bottom here, like this. Okay, we know how to do line integrals now, so you can think about how to do those. I say E, in this material, this is going to be E1. The tangential component of E1 is going to look like this. I'm sorry, I don't have the direction correct. The tangential component of E1 is going to look like this. And the tangential component of E2 is going to look like this. the orientation of the electric fields are shown in this diagram here, E1t and E2t. So our dl in this case, we are moving from A to B. So imagine if this is the x-axis here. Let's say this is the x-axis and this is the y-axis. Then the dl is going to be x hat dx. And our electric field is going to be equal to negative E1t. So you take the dot product of these two. The electric field is pointing in the same direction, the tangential component of the electric field. Dot that with dl. You get E1t time. Here, let me do this. So the electric field is E1t in the x hat direction, and then you're going to dot it with x hat dx, right? So when you take the integral of this going from A to B, you're going to end up with E1t times delta L, which is the x coordinate of B minus the x coordinate of A. So it's the tangential field times the length. You get the same thing on the second integral, the tangential component times the length. And notice that there's a negative sign here and a positive sign here. All right, so as a result of that, you solve this equation and you find that E1t is equal to E2t. Okay, and I recommend if you have doubts about this, you can go through the math yourself. I showed you a quick example of how to do one of those integrals. Okay. Quick question, are you all able to hear me? Okay. Some students were saying that they had some difficulty hearing last time. Okay, good. All right, so this is how we derive the first rule. The second rule is rho s equals d1n minus d2n. And in order to derive this, we need to use Gauss's law. So let's do a quick recap of that because you will need to know Gauss's law for your exam. So Gauss's law is a way to find the electric field. All right, there's three forms of Gauss's law, the differential form, the integral form, and the second integral form here. This is the one that we're going to use right now. What the integral form says is the following. So let's say you have some kind of surface, all right, and normally it's going to be a surface that has some kind of symmetry. For example, a sphere has symmetry associated with it, or it could be a cylinder. So in this volume, the volume enclosed by the shape that you've drawn, Q over epsilon is the total charge contained in that volume, and E dot ds is the surface integral on that closed surface. Okay, E dot ds on a closed surface is equal to Q over epsilon. That is the Gaussian, the Gauss's law that we're going to use right now. So let's jump back down to this slide. So in this case, our Gaussian surface is going to be a cylinder. And that cylinder you can see right here. Okay. Now, like before, we are going to assume that the sides, the length of the cylinder, is equal to h. And we're going to make that h go towards 0. Okay, so this the cylinder is going to become short and fat. All right, so when we do that, the surface integrals on the sides of the cylinder go away. So remember, like in Gauss's law, you have to take the surface integral. Take the surface integral of E dot ds is equal to Q over epsilon. This is the surface integral on the closed contour. So the surface integral is going to be composed of the surface integral on top plus the surface integral on the bottom plus the surface integral on the sides. All right, so what we're saying here is by making h go to 0, the side component of the surface integral, this will drop out by making delta h go to 0. So we're only taking the surface integral on the top and on the bottom. Okay, so that's where we're getting this. So this is Gauss's law here, a slightly different form here, right? Because d is equal to epsilon e. So, and if you use that, you'll get this form that I'm showing up here. Q over epsilon is equal to E dot ds, the surface integral. Okay, so we are taking the surface integral just on the top and the bottom. And it turns out if you do the math here, the surface integral on top turns out like this, and the surface integral on the bottom turns out like this. So d1n dotted with n2 times delta s on the top, and d2 dotted with n1 times delta s on the bottom. You can go through these steps yourself using the same Gauss's law process we used before. It'll be a good way for you to review Gauss's law. And when you evaluate the integrals, you end up getting d1n minus d2n times delta s is equal to rho s times delta s. Remember, Q is equal to the surface charge density times delta s. Divide both sides by delta s, and you end up getting this rule here. Rho sub s is equal to d1n minus d2n. So the normal components of the electric field. Remember, just something to remember is d1n. Hold on, let me erase this. Another way you can write this, if you want to write this in terms of the electric field, you can say epsilon 1 E1n minus epsilon 2 E2n. This is equal to rho sub s. So both of these forms are equal and valid, right? Because d is equal to epsilon e. So those two rules you're going to use quite a bit when you're looking at fields and interfaces. I'm just putting this slide up here. I have this in the notes so that just a review of how you calculate the tangential and normal components. We won't spend time on it right now because I'm assuming that you already recall how to do it. But this is a slide from before. So refraction at a dielectric interface. So I'm going to write down the two rules again. E1t is equal to E2t, and then rho sub s is equal to, we can write this down here, d1n minus d2n. All right, so the polling question, this example, there's two parts to it. There's a solution that we're going to calculate later, but before that we're going to have a polling question. This slide talks about refraction at a dielectric interface. So imagine that you have an electric field 1, and it's in a certain type of dielectric material. It's coming in to the interface at an angle 1. So this is the interface here. This is n hat. This is the surface normal vector. So this is coming in at a certain angle. And when it goes into the other material, the angle changes. Alpha 2 is not equal to alpha 1. So light electric fields, they can bend when they go from one material to another. So in this example, we have a charge-free interface. So in this particular problem, this is equal to 0. So just using these two relations and your own logic here, I would like for you to figure out, think about, is epsilon 1 greater than epsilon 2, which is larger in this case? Assume epsilon 1 is greater than epsilon 2. Is alpha 1 greater than alpha 2? Or are both equal? So I'm going to put this as a polling question. A, B, and C. You guys can think about this for a second. We don't need to rush this one. So I'll give you a couple minutes to write it down yourselves and see if you can figure it out. So my suggestion is that you actually write out the two rules and think about these fields coming in and see how how does alpha 1 and alpha 2 relate to the tangential and normal components. So I'll give you a minute to think about that. All right, let's a little bit more time for you to think it for a few of you. All right. Okay, we have equal split. Nine folks said A. 7 folks said B, and 4 folks said C. All right. So this is probably a tricky question because it seems like we have a equal distribution or close distribution of answers. So let's look at why this is the case. You can we'll go through this ourselves here. I'm going to erase this ink on the slide and just write it over again. So these two rules, E1t is equal to E2t. Okay, so we have a situation where epsilon 1 is greater than epsilon 2, but let's write out 0 is equal to d1n minus d2n. Okay, so d1n is equal to d2n, and the other way we can write that is epsilon 1 e1n is equal to epsilon 2, oops, epsilon 2 e2n. Okay. Now, the way that we can kind of think about this is, without drawing this, I'm going to draw it again here. First of all, the conclusion that we draw is we know that epsilon 1 is greater than epsilon 2. All right, so epsilon 1 is greater than epsilon 2. In order for these two things to be equal, say if epsilon 1 is greater than epsilon 2, then in order for this relationship to hold true, E1n has to be less than E2n. All right, then we can kind of draw it out. So think about it. So E1n is less than E2n, and E1t is equal to E2t. So the way you kind of think about it here, we draw this out. All right, and so we can say that E1n is going to be very small compared to E2n. So let's draw E2n like this, and we'll draw E1n like this. The tangential components are the same, so let's make the tangential components equal to each other. Oh. Right, so this is E1t, E2t. Tangential components are the same, but the normal components are different. So think about this being alpha 1, alpha 2. So in this case, you can see from this little diagram that we've drawn, an exaggerated diagram, we can see that alpha 1 is greater than alpha 2. So the correct answer here is A. Right, so this is a little bit of a geometry problem. Now the second part here is if the two media have a dielectric constant, determine an equation relating alpha 1 to alpha 2. And I will just show you the result here is tangent of alpha 1 tangent of alpha 2 is equal to epsilon 1 over epsilon 2. And the way that you do that is just by looking at this diagram real quick. The tangent of alpha 1 is equal to E1t over E1n. The tangent of alpha 2 is equal to E2t over E2n. The ratio of the two, the E1 and the E2 cancel because they're equal to each other. So tangent of alpha 1 over tangent alpha 2 is equal to E2n over E1n. And this turns out to be equal to epsilon 1 over epsilon 2. Because of the second relationship here. Okay, I went through that derivation fairly quickly. That's just in the interest of time here. I want to go through another example also fairly quickly. You can see the dielectric interface type problems. Suppose you have an electric field, E1 is equal to 2, 3, 4, and an incident on a surface with normal vector 0, 1, 0. Calculate E2 and the two incident angles. Assume that epsilon 2 is equal to 3, epsilon 1 is equal to 1, and the interface is charge-free. So actually, I think what we're going to do is I'm going to make this into a... No. I'm just going to show you. I'll have a similar homework problem like this. So the process for solving this problem, remember the process is what I'm always looking for. You're asked to calculate E2 and the two incident angles. So the solution in the way that you solve these problems is that you have this E1 here, and so you want to find E1t and E1n. You want to find the tangential and normal components of this E1. Okay, and this will then allow you to find the tangential and normal components of E2. So we first find the normal component of E1, and the way that we do that is by multiplying this with the unit normal vector 0, 1, 0, and you get this here. I'm not going into the details of it in the interest of time, but I just want to give you the overview on how to do it, because you already know how to find, if you want to find the component of E1 on the normal vector, you take the dot product here. So I'm using these tangential and normal component methods in order to do that. Okay, so I find the normal component of E1, and then I find the tangential component of E1. And remember that the tangential component of E1 is equal to E1 minus the normal component. So the normal component can be found using dot products. The tangential component can be found by subtracting the normal component from the E1. So I suggest that you go over this problem on your own when you're doing your homework problems. It'll just walk you right through it. So you found the tangential component, and because the tangential components are continuous across the interface, now you have the tangential component of E2, which is equal to 2, 0, 4. And then you find the normal components of E2 by using the second rule. So this was using the first rule that the tangential components are continuous, and this is using the second rule. Okay, because it's a charge-free interface, that rho sub s doesn't show up in the equation. And so we figured out the E2t and E2n, and the total electric field is just the sum of the normal and tangential components. So it really becomes an exercise in just vector math. In terms of the angles, the two angles, you you want to find alpha 1 and alpha 2. Alpha 1 and alpha 2 are these two angles, the E1 angle and then the E2 angle, incident angles. And the way you find those is just by using these, again, the dot product relationship, the definition of the dot product. In this case, E1 dotted with N is equal to the magnitude of E1, the magnitude of N, which is 1, so you can just ignore that, cosine of theta, and then you solve for theta. So you use the dot product to find the angles. I'll just write that down here. Use dot product to find angles. So essentially we had a two-step strategy. Decompose electric field into the normal and tangential components. Use that to find the normal and tangential components of the electric field on the other side of the interface. That gives you E2. And now you just find the angles, you use the dot product to find the angles of E1 and E2. Okay, so pretty straightforward plug-and-chug type question. Just need to recall your vector math there. Let's see if we have any questions. Is it related to Snell's law in any way? Yes, John, it's a good point. Thank you for your question there. This is absolutely related to Snell's law. In fact, this is a derivation of Snell's law from the fundamental electrostatics. So yeah, the electromagnetics is really fundamental to so many things in circuits and optics and many different fields that rely on these basic concepts of how electric fields behave at interfaces. So Maxwell's equations, I remember I said a few lectures ago that Maxwell's equations they don't get the same level of credit that they deserve along Einstein's theory of relativity and those kinds of things that are more, I guess, stylish in popular science. But really, Maxwell's equations lays the foundation for almost everything in modern physics. And of course, like I said, a lot of the basic concepts in circuits and optics. It really is foundational. All right, so let's go ahead and, so we talked about the dielectric-dielectric interface. So this was an example of an electric field going from dielectric medium 1 to dielectric medium 2. Now we talk about conductor-dielectric interface. And a conductor-dielectric interface, these are a couple examples. This is in a spherical system where you have a metal sphere, and then you have air around it. And here's an example of a cylindrical system where you have electric fields at a conductor-dielectric interface. So these types of problems actually are pretty straightforward, but very intuitive. Okay, just remember a couple things. Inside a metal, the electric field is 0. All right, so the tangential field outside the metal is also going to be 0. Remember, the tangential field are continuous through the interface. So a few lectures, 2 lectures ago, we said that in a metal, 1 lecture ago, we said that in a metal, the electric field inside the metal is equal to 0. So the tangential component is equal to 0. This rule, E1t equals E2t, says that the tangential component of the field has to be 0 outside of it as well. And the normal components of the field, d1n minus d2n, is equal to rho sub s. That d2n inside the conductor is going to be equal to 0, so you're left with d1n is equal to rho sub s. So just to clarify, this is outside the metal. So E1 and D1 are outside the metal. D2 and E2 are inside the metal. Okay, so D2n is equal to 0 here. That's why it's not appearing in the equation. So the result of this, the intuitive thing that you can remember, and this is good rule of thumb for design, is that the external field is always normal to the metal surface. And this is so fundamental that regardless of what kind of situation you're in, if you have a metal, just remember, if I ever ask you to draw the field lines for a metal, just remember one thing is that the electric field lines are always perpendicular to the surface. You could have positive charges on them. If they're positive, then the electric field lines will point away from the surface. They're still orthogonal. If they're negative, they point to the surface, but they're still orthogonal. Wherever you have a metal, the field lines are always 90 degrees from the surface. And that can actually help you design, when you're trying to design electric fields to have a certain shape, this fact that the electric field is always normal to the metal interface is very, very helpful. So that example also applies in the cylindrical system as well. So imagine that you have a conductive wire inside here, and then outside of it you have this dielectric material. So let's say you have like a wire, and then it's coated with some plastic on the outside, like an insulating material on the outside. You can know that the electric field is always normal to the metal surface. So inside the material, the electric field is 0. Outside the material, the electric field always points normal to the surface. Okay. At a conductor-conductor interface, this is another type of interface. This is where you go from one conductive material to another conductive material. So you have the interface between two conductors. How does a current differ in the two regions? You can start out with two electric field rules. The E1t is equal to E2t. And remember that J is equal to epsilon E. Remember that. J is equal to conductivity times E. That was how we defined current density. E1t is equal to E2t, so therefore J1t divided by sigma 1 is equal to J2t over sigma 2. Second rule is based on the D1n minus D2n is equal to rho sub s, and we can put that in terms of this. Now the important thing with the normal components is that the normal components, by KCL, the normal components have to be equal to each other. So because they're equal to each other, we can have this other rule that says J1n or J2n, J1n or J2n is equal to epsilon 1 over sigma 1 minus epsilon 2 over sigma 2. And this is equal to the rho sub s. So J1n times this quantity is equal to rho sub s. So this was a straightforward derivation, and so was this one. The only thing that we had to take into account here is because of KCL, Kirchhoff's current law. Whatever current goes into a box is the same current that goes out of the box. The normal components actually have to be continuous by KCL. So just remember this, J1n is equal to J2n, and then you have this other rule here that comes out of it. So there's actually 3 different rules that you want to remember for a conductor-conductor interface. Why are you interested in this? Well, you imagine you have a current going from one conductive media to another conductive media, and you want to see how the currents change. So the key intuition here, normal component of current density is continuous. Even if they have different conductivity, they're continuous because of Kirchhoff's current law. All right. So in the last 20 minutes, we're going to talk about capacitors, energy storage, and electrostatic forces. So I think you'll find this quite interesting. This is also very fundamental to the class, is that I would like for you to be able to derive capacitances, and we'll do a couple examples of that. So capacitors are a fundamental electrical element that stores charge and electrical energy. So a capacitor can be considered two conductors holding equal and opposite charge. We've drawn this many times. We've drawn the basic parallel plate capacitor many times, but you can think about a more general situation where you have a voltage. You have one metal plate that could be any shape, another metal plate that could be any shape. One builds up positive charge, one builds up negative charge, and you have these field lines between them. So, in terms of like a surface, you get surface charge densities on on either one, and you get an electric field between them. So as we know, the unique thing about capacitors is capacitors are the electrical energy storage element for circuits. You can store energy in the form of charge. And so what we're going to do now is we're going to talk about how we can actually derive the amount of energy that's stored in a capacitor. We can even derive the capacitance equations for a parallel plate capacitor, the epsilon A over D that you've learned in your other classes. And we'll talk about different examples of different types of conductive sensors. We'll also talk about the forces between these two conductors. You have one conductor that has positive charge, another conductor that has negative charge. There's actually a force between them that pulls conductor 1 and conductor 2 together. It turns out those forces can actually be used for electrostatic actuators, which are very important in things like micromirror arrays. So let's define a few things first. Capacitance, the fundamental definition of capacitance is charge per volt applied. So if you think about this basic capacitor, the amount of, if you apply voltage to it, you're going to get a certain amount of charge. If you double that voltage, you're going to get the double amount of charge. So the charge is linear with the voltage applied. So we can think about this as this is the charge, this is the voltage that's applied to the system, and this is the amount of charge in the system. Capacitors, simple capacitors, behave linearly like this. Okay, Q is equal to CV. Right, so the slope of this line is equal to C, the slope of the line. So that's what capacitance fundamentally is. It's the amount of charge stored per unit volt applied. So it's coulombs per volt. So capacitance is equal to Q over V, so it's coulombs per volt. And that is also called a farad. Okay, so farad is a coulombs per volt. This is the MKS units for capacitance. As we found the electric field at a conductor-dielectric interface, the normal component of the field is equal to rho s divided by epsilon. This is true for any capacitor. So we looked at this because when we were looking at a conductor-dielectric interface 2 slides earlier, we have this rule, d1n is equal to rho sub s. So this is in the dielectric material. So epsilon times E1n is equal to rho sub s. So this is in the dielectric material. Okay, and that's this rule that we have here. Whenever we have this conductor-dielectric interface, where'd my mouse go? Wherever we have this conductor-dielectric interface, the normal component of the field is equal to this, rho s over epsilon. Okay, so if we were to draw this in the diagram, this is our E sub n here. That's being talked about in this equation here. The normal component on the surface is rho s over epsilon. So what we're going to do here is we're going to take this definition of capacitance and take our knowledge of electrostatics and derive the capacitance of a parallel plate capacitor. So as many of you know, this is where we're going for here. Epsilon A over D. I think many of you remember that rule from your circuits classes that the capacitance is equal to the epsilon times the area of the capacitor times the distance between the two plates. So I'm just showing you in this slide how to derive that relationship, just using our knowledge of electrostatics at this point. And this is the type of problem that I would expect you to be able to do and derive during an exam. I know the thought of derivations may be scary to many of you, but I think that if we go through this step by step, then you'll be able to see how it works. and be able to do it yourselves. And you'll have a homework problem on that as well. So our general strategy, if we want to find capacitance, what we do is we apply a test voltage and we figure out how much current we get, and we take the ratio of the two. So if we break that down further, and the first step we do is we're going to apply a voltage to this system. So imagine we just take our voltage source, we put it across there, and we know that we're going to generate some amount of charge Q on the upper and lower plate. So that we know already. The analysis begins is when we find the electric field as a function of Q. Know that there's going to be an electric field between these two elements here. Depending on the geometry, we can find that electric field. The next step is that we then find voltage as a function of the electric field by integrating. V is the integral of E dot dl. So then we now have a relationship of voltage in terms of the charge. So now, so we have V of Q after we did that. So V as a function of Q. And the capacitance is just the ratio of Q over V. So if we have a relationship of V of Q, then it's easy to find the capacitance. In every single problem that you're going to have in a capacitor type problem, there's going to be a key intuition that you have to know as well. You have a general strategy and a key intuition. I think you found this for the electric field problems too. So keep that in mind. Just always think about what is a key intuition for this problem. Well, one of the intuitions we know is that in a parallel plate capacitor, the electric field lines are uniform everywhere. They're the same everywhere, in between those two plates. There is an exception. There are some fringing field lines here on the outside like this, but just, we don't bother calculating those. If you need to calculate those, you have to use a simulator or other more complex models. We're just looking for the electric field in between there. So the first step, we calculate the electric field as a function of Q. All right, and again, you have to think about like a few of the basic relationships that we know. We know that there's going to be a charge that's deposited on the surface of this capacitor, and we know that the charge is going to be uniform. So if the charge is uniform, the charge density is, we can calculate a charge density as Q over A. So rho sub S, the charge density, which is given in coulombs per meter squared, is Q, total charge, divided by the area of the plate. So the area of the plate is shown here. Okay. Then the electric field can then be found as a function of Q based on the rule that we saw here. Electric field is equal to rho S divided by epsilon. So electric field is equal to rho S divided by epsilon, and it's in the n hat direction. It's always normal. As I said, the field is normal to the conductor surface. All right, so that's how you get like rho S over epsilon. It's z hat. Okay, this is our z axis here. Just circle that for you. So it's in the negative z hat direction. And rho sub S is equal to Q over A, so you substitute that in here. Great. First step done, you have electric field as a function of Q. Okay, second step is now you're going to calculate the voltage as a function of Q by integrating the electric field. This is another relationship that we know. The voltage is equal to the integral from the low potential to the high potential of E dot dl. Whenever we have integrals like this, we have to break it down. What is our E? What is our dl? All right, so I can just make a side note here. And we already have our relationship for E, but our dl, we're going to be integrating from the low potential to the high potential. So we're going to integrate from this low potential plate to the high potential plate. So our line integral is going to go from here to here. Okay? So it's going along in the z direction. So our dl is equal to z hat times dz. Right? So we take the dot product of the two, Q over epsilon A times z hat times dz times z hat. Okay, and we get Q over epsilon A times dz. You integrate that from z equals 0 to z equals d. That's the distance between the two plates. And this is how you get voltage is equal to QD over A epsilon. So now you have voltage in terms of Q. Once you have this, the last step is super easy. C is equal to Q over V. So Q divided by your equation for V, which is in terms of Q. The Q's will cancel here, right? And you're left with just this geometric term, epsilon A over D. So this is the derivation of a parallel plate capacitor. Okay. So the next thing we can do is derive the capacitance of a coax capacitor. So this is maybe a relationship that you don't know. But the point I try to make here is that the same strategy can be applied to the coax capacitor situation. I want you to see how that works here. All right, the coax capacitor looks like this. You have a cylinder, you have a wire in the middle, that's called the inner conductor. And then you have a shell on the outside, and that's called the outer conductor. You apply a voltage between the inner shell and the outer shell. The length of the wire, the length of the capacitor is something like L here. And then you have an electric field that's pointing from the positive surface to the negative surface. So it's pointing from outwards to inwards. Okay. Now the difference between this problem and the previous problem is that in the previous problem, the electric field was the same everywhere. So the key intuition that we have to know in this coax problem is that the cross-sectional area and the electric field depend on the radius r. They're not constant in space. The electric field is weaker on the outer portions of the cylinder, and they get stronger as you go over to the inner portions of the cylinder. Right, the field lines are more concentrated. Right, so that's a key intuition that you need to know. But the general strategy is the same as before. You apply a test voltage and you get a resulting charge. Find the electric field as a function of that charge. Then find the voltage as a function of the electric field, and then the ratio, C is equal to the ratio of Q over V. So we apply the voltage. We assume that there's a charge at the inner, plus charge at the inner, minus charge at the outer, just like it's shown in this diagram. Find the electric field as a function of Q. And we use Gauss's law to do that. All right, so rho sub S, the surface charge density. So we know that we have a total charge Q. Just like before, we want to find a surface charge density, just like we did on the other capacitor problem. So rho sub S is equal to Q divided by A. Okay, and this time, notice the equation for A. Q is equal to Q divided by 2 pi RL. The area of the cylinder, the cross-sectional area of the cylinder, is 2 pi RL. This is a function of R. So if you imagine drawing a bunch of cylinders going from the inner conductor to the outer conductor, these cylinders get larger and larger as you go from the inner conductor to the outer conductor. So the area, the cross-sectional area of that cylinder is changing. Right? That's why this is a non-constant cross-section. And so the charge density, instead of being uniform, the charge density is a function of R. So you have a low charge density on the outer cylinder and a higher charge density on the inner cylinder. Okay? So that's a key difference between the parallel plate, which has uniform charge density, uniform electric field. The coaxial capacitor has low charge density, low electric field on the outer conductor surface, and a higher charge density, higher electric field on the inner conductor surface. And the electric field turns out to be a function of R as well, because you plug in the formula, E is equal to rho S over epsilon n hat, same as before. And you get this relationship, rho S over epsilon times R hat, and you plug in the surface charge density that you found here, and it's Q over 2 pi RL epsilon in the R hat direction. All right, we are at 209, so I'm just going to finish up this derivation, and then we're going to have to finish up the rest of the stuff in next class. So finding the voltage as a function of the electric field. So that's the second step here. So we notice that our electric field is R dependent. So inside, when you have small r, the electric field is going to be strong. At large r, the electric field is going to drop. So now we have to find the voltage as a function of the electric field. So we're going to follow the same idea. You're going to integrate the electric field from R is equal to B to R is equal to A, because you're going from integrating from low potential to high potential. All right, that's our procedure when we integrate voltage. Go from low potential to high potential. So the lowest potential is when R is equal to B at the surface of the inner conductor, and then R is equal to A at the surface of the outer conductor. E dot dl. All right, so so when you integrate R is equal to A to B of E dot dl, the electric field you have here, and I'll just write down that dl is equal to R hat dr. In the previous example, it was Z hat dz. In this example, it's R hat dr. We're going in the radial direction. So you take the dot product of those two, E dot dl, and then you end up with this, Q over 2 pi L dr over R. When you take the integral of dr over R, you get an ln term. So that's where this ln of B over A comes from. Okay, now that you have a relationship for voltage in terms of the total charge Q, then the last step is straightforward. C is equal to Q over V, and you come up with 2 pi epsilon L divided by ln of B over A. So this is the capacitance per unit length of a coaxial capacitor. Okay, a lot of integration steps here, a lot to think about in terms of geometry, intuition. This is why electromagnetics is tough, right? But if you go through this, I suggest that you go through these derivations on your own, step-by-step process. Convince yourself that this general strategy works, regardless of what kind of system that you have. And we did an example of a Cartesian coordinate system, and this is a cylindrical coordinate system. Do one in a spherical coordinate system. You may have that as a homework problem or as a test question. Right? There's only 3 coordinate systems that we work with, right? So there's a limited set of problems that I could think of, right? So we've had problems like that in the past. Okay, so we are a couple minutes after class. Thank you for your attention. I know that many of you have to go. So what I'd like to do is just mention to you that there is going to be a homework assignment that is posted tonight, and that homework assignment will be due next week. Next Monday, we will have one more final assignment that's going to be due 2 weeks from today, and that will be it for this class. You know, we're coming up to the end of class. Our final exam is going to be 2 weeks from Monday. So the plan for the rest of the class is Wednesday we are going to finish up the electrostatics chapter. I was hoping to finish it today, but we'll finish it Wednesday and get started on magnetostatics. We'll have a couple lectures on magnetostatics, and that will be it. We won't be able to get into the time-varying fields this semester due to time constraints. So some of you are asking, is it possible to move the final exam because we have linear exam on the same day? That may be tricky because the university guidelines is for us to have the final exam at the regularly scheduled class time, unless you have more than 2 exams or more than 3 exams in some 72-hour period. That being said, so Pooja says most of us are in that class. The only way I could really change the final exam time is if we have 100%, if we have 100% unanimous decision on a certain time that works. That's the only way that I could make it fair to everybody in the class. And so if there is a time that works for everybody, I'm willing to move it, but it has to be unanimous, meaning there can't be a single student, every single student has to be able to make it at that time. So if you all want to discuss by yourselves within the discussion boards, you're welcome to do that. I'm also willing to help out with a doodle poll if that is helpful. and we can kind of go from there. Let's make that discussion. We'll try to figure that out in the next. Noor is saying, please make a poll. Yeah, so I'll do that. So I understand that your linear exam is on that Wednesday. So let's go with that. Let's now, for all of you who have to go to a different class, feel free. For the rest of you who would like to stay on for our virtual office hours, what I'd like to do is, I think this particular conference is going to close after 2 hours. So we're not limited to that. I'm going to start another conference. So we're just going to go off and log off this conference and start another one that's going to be office hours. And so just look for that, and we can just go over the questions as we see fit. Live Q&A session. Okay. So so in terms of the regular lecture, we will end here. And I'm going to stop the recording here, and I'll also stop. I'll log off from the lecture. So I'm going to create another conference in just a minute or two. So just log back onto that one. Okay, and I'll see you all in a little bit.